Thank you very much for the introduction. Good morning, everyone who is following this presentation west of Italy, and good afternoon to those who are over here, and good evening probably to those who are further east. So this paper that I'm presenting today, the work is co-authored by, as you see on the screen, by Enrica and Ian, who are both my supervisors, in addition to Francesco, of course. And this is one of the chapters of my dissertation. So my interest in the PhD dissertation overall is looking at the impacts of climate change on agriculture using empirical approaches. And in that dissertation, I focus on building statistical emulators, but that is at a global scale. And this particular paper focuses today on US agriculture. So without much delay, I'll start the presentation. This will be the outline of the talk today. I will spend a bit of time on the background, the motivation of the study, the methodology. I'll introduce a few key results of this paper. Due to time constraints, I won't be able to discuss all of them. And then I will summarize these results with some scope suggestions for further work. Okay, so I don't think we need to justify further why agriculture is probably the sector which is going to be or likely to be most affected by climate change in the future. This has been emphasized strongly in subsequent Intergovernmental Panel of Climate Change Assessment reports. Arguably, it's one of the key sectors. And in order to assess the impacts of climate change on agriculture, what we currently, or the researchers typically use, are crop models, which are currently the best tools available for us. And at a global scale, at a global crop modeling exercises that are currently underway, two key exercises that I will mention over here, mainly because the data comes directly from these crop modeling exercises. This is the AgMIP, the Agricultural Model Intercomparison and Improvement Project, which is sort of an umbrella project overlooking the second one, which is the Intersectoral Impacts Model Intercomparison Project. So both these projects, basically, they bring together a lot of experts from crop modeling background. They ask them to run their own crop models under different setups. So you have their default setups where the crop modelers are asked to run the simulations that they typically use for their models. And then you have some harmonization where they are given the same set of input parameters, soil conditions, crop growing seasons, and so on. And they are asked to repeat those simulations. So the idea is to come up with a broad range of projections which can be useful for policy implications. And I will spend a bit of time over here to explain typically what are the types of crop models that are used in literature for examining the impacts of climate change. So broadly speaking, the crop models can be classified as two. The first one being mechanistic or process-based. So these are numerical crop models, much like your numerical climate models. And the second one is based on statistical principles. Now, as Lobel and Asanga recently highlight, that the distinction between these two is not perfect, in the sense that in process-based crop models, you do have a lot of calibration, which is based on statistical approaches. And on the other hand, in statistical crop models, you tend to be biased towards certain processes, and you choose your statistical parameters based on that. So there's not a very clear distinction between two, but this is what broadly the crop models are classified as. Further down the line, the process-based crop models are typically either site-based, where the calibration is done at a field scale, or you can have agro-ecosystem-based process models, wherein they focus more on the carbon and nitrogen dynamics and the feedbacks. Irrespective of which of these crop models, the current generation of crop models that we have are at a global gridded scale. So typically they are at a fine scale resolution of ½ degree, and they cover the entire globe. And these are typically known as, in short, as GGCMs, similar to your GCMs as global climate models. So what do these processes that are actually going into these process-based crop models? There are a lot of them. Primarily, they are the knowledge of individual crops, the soil conditions, weather, of course, what are the management practices that the farmers adopt, and so on. So there's a lot of detail going on in these kind of crop models, and they are quite computationally expensive. The advantages are that some of them are also capable of simulating the impacts of pests as well as carbon dioxide fertilization effects and ground level ozone. Carbon dioxide fertilization effect in particular is quite important because under global warming conditions and high concentrations of CO2, you can have some negative impacts that are being offset by carbon dioxide fertilization effects. The process is quite detailed. I will not go much into it, but just to give you a broad introduction about these kind of models. And what do they do, these process-based crop models? They use these input parameters, and they basically are numerical models. So the main output that they generate are the crop yields amongst other outputs, which are actual evapotranspiration. So how much water is being evaporated from the leaves of the crops as well as from the soil. So this is evapotranspiration. But what we are mainly concerned with these crop models is the output, that is crop yields, that is generated. Then we have on the other side the statistical models, which typically use a functional form between the observed crop yields and the observed weather. I say weather because these models are typically calibrated on daily or monthly weather data and not a long-term mean climate data. So if the data comes from observed yields, historical observed recorded yields, then these models are known as empirical models. On the other hand, you can also have the statistical model calibrated on the crop yields that are coming from the process-based models, and these are known as emulators or surrogate model, or basically an approximation of these process-based models. So these are the two kinds of statistical models that you come across in agriculture and in the agronomic literature. Just to give a framework of the statistical models, because I think it's important to introduce them over here before I go further with the methodology and the results. Typically, these statistical models can be based on three types, either time series, cross-sectional, or panel data. So in the first one, in the time series, you typically have data for a single location, but for multiple years. In the cross-section, you would have data for a particular time, a particular year, but across different locations. Whereas in panel data, as you can see from the subscripts, it's INT, which indicates that you have multiple observations for this different locations. Irrespective of which of these, methods we use, the fundamentals are quite similar. However, I focus here on panel data because this is what we have used in this paper. And panel data is also the more popular choice, ideally because it can control for variations both in time and space, as well as control for the omitted variable bias. So just to focus on the specification over here, typically the dependent variable is the natural log of crop yields at the location and a particular time, so the year in this case, because most of the time we focus on annual crop yields. Then you have the set of the vector of predictors, which are typically temperature and precipitation, and they are higher forms, again at the location and the time. The next term is a location-specific intercept. So this is basically individual intercept for each location, and this is known as a fixed effect. The next one you have is the time effects or the time trends. The time effects or the time trends basically capture the technology trends, whereas the location specific effects are meant to capture time invariant characteristics. So if, for example, if you have soil characteristics that are not varying over time, these are captured by this term. And finally, you have the random disturbance term. And what do we do with these responses that are coming out of either process-based or statistical models? Well, they go into your integrated assessment models, which are then used for broader analysis of policy framework. Now, coming to the motivation of this study, there are quite a number of studies already done on both these process-based and crop models and the empirical crop models. So we need to see where the literature is lacking, and we find that there are actually very few studies that look at a comparison between the two, as well as a comparison between the methods and the individual models. The key questions, few quick key questions that we ask over here are these global gridded crop models able to replicate the observed characteristics of the crop yields? And if not, what actually drives this divergence in the results? And what can these divergence in the results mean for future? What are the implications under future climate change? What we are not trying to do over here in this study is address the question of benchmarking the crop models, or to say which of the two methods are superior over the other. For this study, we are focusing on United States counties, but the rain-fed counties. So typically these rain-fed counties are east of 100° west meridian. Just a quick introduction on the county. So county in the United States is an administrative unit within a state. The size varies. The largest is approximately 52,000 square kilometers, and the smallest is 32 square kilometers. We focused on 3 rain-fed crops: maize, wheat, and soybeans. We look at the annual yields in tons per hectare. The observed data comes from the US Department of Agriculture, USDA, and this is at county scale, aggregated to county. And our data from the crop models that we utilize come from the ECMIP fast track. So the ECMIP crop modeling simulation that I mentioned earlier. The 6 crop models that we used are all at half-degree resolution, gridded resolution. So this works out to roughly 3,000 square kilometers. We employ a panel data approach where we have panel data for 33 years. Depending on the crops and the models, the counties, the number of counties utilized in our study range from 1,200 to 1,800. So we have approximately 35 to 50,000 observations in our study for each of these crop models and crops. For both these crop models and the observed data, we employ a fixed crop growing season, which is defined from months May, June, July, and August. So this is United States we are talking about, so it's in the northern hemisphere. And typically most of the crops over there, barring wheat, which is grown throughout the year, is ranging from May to August. Now, to put the size into perspective, what scale are we looking at this? Is, if you're familiar with the province of Verona, so you can think of our study is looking at that scale. So we are running regressions for basically data aggregated to that spatial scale. To introduce the 6 crop models that are used in this study, these are process-based. There is quite a lot of heterogeneity across these models. First of all, the type, so they can either be site-based or agroecosystem. In fact, one of them is based on agroecological zones. Then you also have the problem of what they are actually simulating. So some of them simulate actual yields, whereas some simulate potential yields, which are unlimited by nutrient constraints. Some of these crop models also have endogenous adaptation, so they allow for the cultivar to change in their simulations. They also allow dynamic planting dates, so not only the planting season varies, the window of the planting season, but also the actual dates. And last but not the least, so these are the key parameters. These are not the only ones which are varying across these crop models, but the important ones that I'm showing you. The two other important ones are the heat stress, which is explicitly modeled by crop model Pegasus. So heat stress is typically how do extreme temperatures affect yields in a growing season. Some of them are not calibrated at all, so the crop models that are simulating this data are not calibrated to national or site-specific yields, whereas some of them are calibrated. So this is one of the issues we face with these kind of modeling exercises, that if there is no harmonization, which is what is happening in ECMIC fast track, the first set of data, you are thrown on the table with different models, different types of models, different types of parameters that are going in them. For this study, what we do is we begin a comparison of the simulated yields by these crop models with the actual observed yields from the USDA data. And we focus on the historical period, which is defined as 33 years of 1972 to 2004. So this is our first comparison on how well do these crop models actually perform. Then what we do is we use the weather variables, daily temperature and precipitation, from HADGEM to Earth System model. The reason we choose this model is because from the ECMIC fast track, the data that we use for the crop models are actually driven by this Earth System model. So that this is the actual driving input weather parameters. We use this daily temperature and precipitation, and for both the process-based models and the observed data, we come up with a reduced form response function. So if you look at the one which is over here for the crop models, this is typically an emulator, and this is your empirical model. Our next comparison is for both these emulators, the response functions, as well as for the one derived from the observed yields, which is the empirical model. Then we use, again, the climate data for future RCP 8.5 scenario from the HADGEM model for 2 different periods in the future. So 2 different mean periods, and we come up with the projections. So we compare the relative changes in crop yields, so the percentage changes in crop yields, as estimated by the emulators and by the empirical model. So broadly speaking, there's a 3-stage comparison in this study. Okay, the first comparison, direct comparison between the crop models and the observed yields. Because these crop models lack harmonization, some of them are calibrated and some of them are not, whereas some simulate actual yields and some simulate potential yields, we cannot do a pure apple-to-apple comparison. What we need to do is we need to devise a methodology to normalize both of them. So we are characterizing the distribution now of the differences between what the crop model simulated and the observed yield anomalies. Now, when I say yield anomalies, it's basically for each crop model and for our observed data, what we do is we take for each county and each year the yields that are simulated by the crop model, and we basically normalize it in this way as a fractional deviation from the long run mean. So the long run over here is our historical period, 1972 to 2004. And this is done for each crop model as well as for these data from the observed, that is the USDA. We then look at the difference in these yield anomalies, and then we examine the distribution. So ideally, the perfect score for a perfect model would be 0. So if this difference is 0, the crop model is doing excellent in simulating historical yields. This is the first figure, which is basically showing you on the x-axis the difference in the yield anomalies between the crop model and the observed. The y-axis is showing the counties, so the number of counties. Each light line over here represents individual year, so the 33 years, and the distribution of the counties. The thick solid line is basically the mean of these 33 years. So we should be focusing on the thick solid line for interpretation. The 6 crop models are shown over here, color coded. I'll just show you the other 2 crops at the same time for wheat and soybeans, for which the distribution is not very different. And what we are interested to see is whether there is a peak at 0. So for each of the crops and the crop model, what we want to see is ideally if the distribution is peaking at 0, this thick line over here. And what we find is that barring crop model image and to a certain extent LPGML for wheat, the models perform quite poorly in simulating the yield anomalies. Oops, sorry. So we try to examine what could be the reasons for this as I go further ahead. The second method that we use is to look at how these crop models respond to the crop growing season temperature and precipitation. So what we do is we use this econometric specification for the panel data. So the one I showed you earlier, where our dependent variable is the log of yields. Then we have our predictor variables, x's. We do this for each crop model as well as for a multi-model. So this is a panel spanning the 6 crop models. So you have the crop model dimension over here also, a dummy over here. We look at the cumulative exposure to intervals, which is the temperatures and precipitation as bins coming from the Hedgem model. And these bins are defined as the intervals between typically 2.5 degrees temperature and 5 degrees intervals of precipitation. So we end up having 10 temperature bins and 3 precipitation bins, so a total of 13 predictor variables, in addition to the fixed effect and a time dummy, or capturing the time varying characteristics. What we do is we first look at how well our econometric specification is able to capture the cross-sectional time series variation in yields. So this is the adjusted R square for only the x's, so not taking into account the fixed effect terms. And as you can see, for the empirical specification, we have a good amount of variation that is explained by our predictors, our specification. But we have some issues over here with a crop model image as well as for wheat. In general, wheat is not very well captured by our specification, and one of the reasons is that because wheat is grown outside the crops growing months that I mentioned, May to August, we believe that the response of yields to temperature and precipitation is not well captured over here. For image, since I already mentioned this crop model twice, let me just say that this crop model uses, for its own calibration, historical yields that are coming from Food and Agriculture Organization. It also simulates yields in 5-year time. So it's not annual yields, but every 5 years. And then to fill those gaps between the years, it does a linear interpolation. So there's not a lot of interannual variability in the yields as simulated by image. And perhaps that's one of the reasons that our specification is not able to capture this model very well. So what do these responses look like? So what does this mean to the crop yields for every additional day in a particular exposure bin of temperature and precipitation? So here what I'm showing is for each of the 6 crop models, which are colored over here, along with the multi-crop model panel. The y-axis is the log yield response. So to interpret it is a percentage scale. And what we are looking at on the x-axis are the temperature bins over here. So holding this particular temperature bin between 22.5 and 25 degrees Celsius, it shows that there is a positive yield response to that temperature in this range, which is between 7 and 22.5 degrees for most of these crop models. There are a few which have negative impacts. On the other hand, when we know that typically for crops, there is a negative response to temperatures beyond 25 degrees, it shows a well-pronounced negative impact. However, when we look...
Malcolm, this is the moderator. Yes. You have 5 minutes more or less to come up to the conclusions.
Okay. All right. Okay, so what I wanted to show over here is typically that, in short, the crop models have a very amplified response to temperature and precipitation, whereas the observed, which is this gray one, they have quite muted response. So basically, crop models are more sensitive in how they simulate the response of yields to temperature and precipitation, and this is fairly common for all of them, as well as all 3 crops. This, when translated to yield impacts in the future, basically means that on an average, the crop models tend to be more pessimistic compared to the empirical model, at least the data from the crop models that we are using. So I don't want to say all the crop models in general, but the particular crop models that we are looking at and from this particular simulation runs. Of course, there are some outliers. So for example, image is quite optimistic, and also model Pegasus, which shows some benefits, positive yield changes in northern part of United States. Okay, lastly, we look at what the divergence is. What are the reasons behind this divergence in the results? And to do this, what we do is, basically, we go back to our table I showed earlier, where we have the heterogeneity across the crop models. So these parameters, and we do a dummy coding. So basically, the dummy variable is 1 if that particular parameter is implemented in the crop model, and 0 otherwise. We then simply run an analysis using the dependent variable over here as basically the difference in the coefficients of the crop models, so the betas of the crop models, and we observe. We use this as our dependent variable, and we use the dummies as our explanatory variables over here. And what we are interested to see is how much of an effect these dummy variables are having, how much of a role they play in the divergence of the results. What we find is that heat stress, which is one of the parameters in crop models, plays a significant role in reducing the difference, the divergence between the crop models and the empirical model. And this is actually in only one of the crop models. The heat stress parameter is actually used in only one of the crop models, which is Pegasus. And as you can see, it tends to pull the responses of temperature to agree more in line with the observed. There are other parameters which also play a role, namely cultivar change and dynamic planting window, which are basically the adaptation within the crop model. So they also have an influencing effect on how the results, on what drives the divergence in results. Now, this particular thing is not done in literature as far as we are aware, so it is quite an important step to help the crop modelers understand why the results vary with each other as well as with the statistical models. I'll just come to the results. So I have just 2 slides. The key finding of our work is that crop models are the anomalies, the yield anomalies, are not really in agreement with the ones we see observed for the US counties. So again, I'm specifying these results are for US counties. It cannot necessarily be taken outside the context of the field of study. We also have to remember that these crop models are not optimized for US agriculture. So these are global credit crop models. So we have to keep in mind that they are not really optimized only for US counties. We find that the main driver of this divergence is the crop response function itself, so the set of parameters that they use, and not so much with the choice of the climate input variable. So this is a sensitivity check we did, and I did not present these results, but this particular choice of climate input variable, so whether we are using a HatGem model or some other, is secondary. In general, the crop's sensitivity to both temperature and precipitation is a bit amplified compared to the observed. However, the response curve is fairly well replicated. So we have optimum growing temperature between 10 and 22 degrees, which is well captured by the crop models. Precipitation is not fairly well captured, but this is a problem across all the crop models as well as in the empirical. What drives this, again, divergence is the choice of management practices, length of the crop growing season in the crop models, adaptation strategies. And finally, the implications. We observed that across the 6 crop models, broadly, most of them project negative impacts of climate change on crop yields. These impacts vary. Some of them are quite pessimistic, some of them are optimistic, but broadly speaking, they project negative impacts. And again, the divergence in the drivers which are responsible for this divergence are heat stress and the adaptation. So in most of these results, I've been emphasizing on heat stress and adaptation as the key parameters that are in the crop models, which are responsible for the divergence of results. As I mentioned, the crop models are not optimized for US counties, and also our choice of crop growing season can influence the results, especially for wheat. However, further sensitivity checks that we do, we find that the results are not overly influenced by the choice of the growing season. It would be interesting to expand the study where further observed historical data is available, namely in India at district scale and from the last presentation that David made over here in Spain. And what's probably most awaited is the next set of simulation data that will be available soon, coming from the phase 2 of the AgMIP and ECMIP exercises. So this simulation data will be more harmonized, so we will have a better understanding of what is going in these individual crop models. And it will help us to lay sort of a benchmark for the skills of these crop models. Just finally, I would like to acknowledge, apart from the two co-authors, my supervisors. Thank them for this study, as well as the two people from AgMIP and ECMIP, Joshua and Christoph, who provided a lot of better understanding of what these crop models use in their simulations. And with that, I end my presentation. Thank you very much for the opportunity.